Hello all, welcome to this new session in this course on time series modeling and forecasting using R. Okay. Now again, just to quickly revise or just to tell you as to where we stopped in the last lecture. So again, the focus of the last lecture was kind of revolving around this idea of model identification, right. So we'll kind of extend the same idea in a bit more slides and then we'll talk about a slightly newer kind of a idea. Okay. Now again, just to give you a brief idea about what exactly you mean by model identification is that, let's say if you're working with a practical data and if you want to fit some time series model on that practical data, then how do you identify the particular model which could be fitted on the data, and once you identify the model, then how do you specify the underlying orders of the model. So let's say if you're fitting an ARMA model or ARIMA model or SARIMA model, right, and so on and so forth. So how do you fix the underlying orders of these models? Precisely how do you fix P and Q, right? And the last lecture we saw multiple ideas. So the first idea was based on some visual plots, right? So ACF plots, PACF plots, and then the underlying tendencies in both the plots, right? And then later on in the later half of the lecture, we talked about information criteria, if you remember. So let's say Akaike's information criteria, which is AIC, or Schwartz Bayesian information criteria, or SBC, right, or Hannon and Quinn information criteria, or HQIC, right. So let's say if you have a pool of models that could be fitted on the data based on, let's say, some visual checks or some other technique, then how do you proceed with identifying the best model? Then this is exactly where the information criteria come into picture, right. And again, just to summarize the idea of all the information criteria, so be it AIC, SBC, or HQIC, the idea is that one should always tend to minimize the information criteria as much as possible. Okay. So let's say if you have ARMA 2.2 and then ARMA 2.1, and then you want to compare that which model could be slightly better, then you find out the AIC for both the fits, and then whichever AIC is the least or whichever AIC is minimum, you go with that model. Okay. And I think last lecture we talked about one idea which was based on sample inverse autocorrelation function, or SIACF, right. And then we talked briefly about a couple of advantages of such a function, which is SIACF, and one of the important advantages was that it kind of prevents or it kind of detects over differencing. Okay. So again, in today's lecture we will kind of extend that, and then we will propose one more idea which is based on this extended sample autocorrelation function, or ESACF, right. So last class we talked about SIACF, and then this one is ESACF. Okay. So the advantage of applying such a function is that the extended sample autocorrelation function, or ESACF, can tentatively identify the orders of a stationary or non-stationary ARMA process based on a slightly different idea, which is iterated least squares estimates of the autoregressive parameters. Now probably I'll pause here just for a second, and then again if you go back to the last lecture, the main idea of how we estimated the parameters were based on MLE entirely, right, or maximum likelihood. So be it AIC or SBC or HQIC, so in all these ideas the estimation technique was kind of similar, which was maximum likelihood estimation, right. But can you somehow find the estimators by changing the technique? So this is exactly what ESACF considers, that rather than estimating using maximum likelihood, can we kind of estimate the underlying parameters based on iterated least squares estimate. Okay. So I think this is the only difference between either AIC or SIACF or SBC and all those techniques, and whether should you go with something like ESACF. Okay. Now probably what we will do is I will show you a table which is a practical kind of an example, and then we will kind of identify that which model is the best one. Okay. So here we have something called as a minimum information criteria, or MINIC. So MINIC, right. So minimum information criteria. So this minimum information criteria kind of uses a combination of AIC and SBC, right. So if you want to evaluate that which model is the best one, you kind of use a combination of AIC and SBC in some sense to minimize the overall information which is there in the underlying model structure. Okay. Now what do you mean by that? So let's say you have an AR kind of a structure, so all these are the orders. So if you see the first row in this table, so the model orders for an AR model are given. So let's say 0, 1, 2, 3 and so on. And if you look at the first row, this is MA, and then just below that you can see the MA orders, right. So, the first column gives you AR orders, the first row gives you the MA orders. So, 0, 1, 2, 3 and can kind of extend, right. Now, so what is the idea about this table here? So, for each pair of orders, so let us say AR0 MA0 or AR1 MA1, AR2 MA2 and so on. So, for each pair I am actually finding the SBC value for that, right. So, SBC is Schwarz-Bayesian criteria. So, I am finding an information criteria, alright. So, and then whatever value I have based on the practical data, I will input that in this cell. So, SBC 0 0 because orders are 0 0, then 0 1, 0 2, 0 3 etc. Okay. So, this table will kind of give you a better idea really quickly as to which cell gives you the minimum kind of a value, right, and then you kind of fix those orders accordingly, right. So, we will see an example here. So, let us say so this table is produced using a software, of course. So, let us say if you are analyzing a practical data set and you get this MINIC table, right. So, again like I said, the first row gives you all the orders for possible MA structures and then the first column gives you all the orders for possible AR structures, right. So, 0, 1, 2, 3, 4, 5 and then similarly 0, 1, 2, 3, 4, 5 for MA as well. Okay. And the values inside this table kind of gives you that MINIC value. Okay. And here the idea is that you want to identify the minimum possible value, alright. So, you want to identify the minimum possible value. And then here you do it using slightly different kind of a technique. So, if you observe all these values, right. So, this software kind of identified this value that you see in red to be minimum in terms of both AIC and SBC collectively, alright. So, this value is minimum based on both AIC and SBC collectively. Okay. And again you can kind of see that this value is in fact the minimum, right, because this is minus 0.03571. So, all the other values are higher than that. Okay. Obviously, many of the values are positive and then you have a handful of values which are negative, for example, this one, that one and then this one, but then even out of those negative values this is the most negative. Okay. But then you should remember one thing, that these values are not just based on SBC alone, but it uses a combination of AIC and SBC. So, here you can see the comment in red that the minimum table value based on BIC 10 is nothing but minus 0.03571 and which corresponds to nothing but AR1 and then MA0 as the orders, right. So, essentially the model using this MINIC criteria comes out to be ARMA 1, 0. Right. Now, again ARMA 1, 0 is nothing but AR model of order 1 because here you do not have any ME component because the order is 0, make sense. So, one can actually implement this MINIC criteria in any software, let us say R or any other software. So, let us say SAS or Minitab or Python, right, to find out which value gives you the least kind of a MINIC value, and then MINIC value is nothing but a combination of AIC and SBC together. Okay. So, this is just an idea about how do you identify models based on some information criteria or let us say some visual plots, etc. Okay. Alright. So, I think now we move a step ahead and then we enter this plethora of different estimation techniques. So, and then what we call as model estimation criteria or model estimation techniques. So, how do we estimate particular models? Okay. So, again after specifying the model orders, right. So, how do you do that? Using some information criteria and so on, right. So, once you specify the model orders, we need to estimate the underlying parameters, isn't it. So, let us say from using some information criteria, you obtained the best orders to be let us say ARMA 1, 2. Okay. So, once you know that the ARMA 1, 2 model is the best in that scenario, then if you remember that equation of ARMA 1, 2, you have certain parameters in that underlying model, right. Now, the idea is that how do you estimate the underlying parameters, okay. So, here we can actually assume that the order is known, of course, and then the model has 0 mean. So, we kind of assume that there is no intercept. So, the overall model has a 0 mean, okay? And this idea could be easily tweaked, by the way. So, even if the mean is not 0, we can do a very simple manipulation or a simple transformation to ensure that the transformed mean is 0. So, what do you mean by that? So, let us say if the mean is not 0, we can always subtract the sample mean. So, y bar is a sample mean and then fit a 0 mean ARMA process. So, let us say xt and then somehow get back to yt by applying this transformation. Okay. So, again just to tell you, so y bar is what? So, y bar is a sample mean, xt is what? So, xt is a zero mean ARMA process. So, xt follows an ARMA process with zero mean. So, there is no mean or there is no intercept there. Okay. So, using this combination you can actually get back to the original time series. So, even if the mean is not 0, you can actually replace that by something like xt plus y bar to get hold of the actual mean there. Okay. Alright, now how about some estimation techniques? So, or in other words, what all are the ways of estimating the underlying parameters in a model? Okay. So, the first one is method of moments. So, in short MOM or MOME. Now, the second one we discussed in the last lecture, MLE, so maximum likelihood estimation, or one can actually go with something called as OLS or ordinary least squares, or let us say least squares estimation, either conditional, unconditional. So, in short you have several different techniques of estimating the parameters. So, method of moments, maximum likelihood, OLS, least squares, etc. By the way, OLS is exactly similar to what we have in the regression, isn't it? So, even in regression we have OLS technique. So, we estimate the underlying parameters in, let us say, simple regression or multiple regression using an OLS technique kind of. Okay. Alright, so now we will probably elaborate a bit more on each of the estimation techniques and then probably see that how exactly can you deploy those. Okay, so now the first one is called as method of moments technique. And by the way, this method of moments technique has a slightly different name also. So, it is called as Yule-Walker estimation, right. So, it is called as Yule-Walker estimation also, but then you have a certain drawback here. So, such a kind of a technique which is method of moments or Yule-Walker works best for only AR models and then not, let us say, ARMA models or ARIMA models and so on, and then for large n. Okay. So, in a way this is not an efficient method, right, because you have a lot of restrictions here. So, works for only AR models and then n should be really large, right. So, in a way or in short, this is not a very efficient kind of a method. Okay. But what exactly is the basic idea underlying this method of moments technique? So, the basic idea is that you simply create some equations, right, and then what exactly are the equations? So, you basically equate the population moments to the corresponding sample moments and then keep on solving for the parameters. Okay. Now, before we go into any of the details, I will give you one very easy example. So, let us say you have a random variable x. So, I will not give you an example from time series because we have one example in the next slide. But let us say if x is a random variable which follows, let us say, some distribution normal with mean mu and variance is sigma square. Okay. And then let us say the idea is you want to estimate both these parameters because both these parameters are unknown, right. So, mean is unknown, the variance is unknown. So, how do you estimate that using method of moments technique? So, for that what we will do is that, or rather what I will assume is that you have a collection of random variables. So, let us say x1, x2 up to let us say xn, right. So, you have a sample basically and then not just one random variable. So, you have a sample x1, x2 up to xn. And then each of these random variables are IID, so independent and identical, and then the distribution is normal. Okay. So, this is the problem. Now, the question is how do you estimate the underlying parameters which are mu and sigma square. Okay. So, here what we will do is again if you go back to this basic idea that we discussed a short while back. So, you have to create those equations now, and then what exactly are the equations? So, the first equation would be you look at the first parameter which is mu. This is the population version of the mean. So, you equate this to the sample version. Now, the sample version is what? Sample version is nothing but the sample mean, isn't it, which is x bar clearly, right. So, this would be my first equation, and then the second equation would be you equate this sigma square to the sample variance. Sample variance is written down as 1 by n minus 1 summation xi minus x bar whole square, isn't it. So, the moment you create these two equations, the idea is that you should solve for mu and sigma square based on, of course, x, because x is the data that you have. Alright. So, the idea is clear hopefully that depending on the number of parameters you would want to estimate. So, here in this case you are estimating 2. So, mu and sigma square. So, the idea is that you create those many equations, right. So, the first equation is mu equals x bar, very simple equation. And then second equation is sigma square equals the sample variance, and then you keep on equating and then solving for the parameters. Alright. So, this is broadly the idea underlying the method of movements technique. So, we will take up an example. So, let us say you have a time series yt, right. So, you have a time series yt. So, expected value of yt would be nothing but 1 by n summation of yt. Now, expected value of yt is a population version, right. So, this is nothing but the population mean, and what you have here is nothing but the sample mean, right. So, 1 by n summation of yt, t goes from 1 to n is the sample mean. So, essentially what you are doing is you are again doing the same thing that we discussed in the last slide. So, you are equating the population mean and the sample mean, which is y bar. So, this would be my first equation, and of course, if you have more parameters, then you have to create those many equations. So, this could be a generalized kind of an equation. So, let us say expectation of yt into something like yt plus k, again this is the population version. And what does this give you? By the way, this gives you the gamma k or the covariance, isn't it? Because expectation of yt into yt plus k is nothing but the covariance, okay. And again assuming that the process has a 0 mean, by the way, alright. Yeah, so, if the process has a 0 mean, then you can actually create this equation, and then the sample version of the covariance is nothing but this, right. So, 1 by n summation yt into yt plus k. So, essentially you are equating the population autocovariance and the sample autocovariance. And similarly, one can actually create equations based on correlations also, right. So, something like rho k equals rho k hat. So, here wherever you see hats, so hats represent estimators every time, okay. So, gamma k hat or rho k hat. So, both these are the estimated quantities, or these are the estimators of the underlying parameters basically, alright. So, in this sense we can create those many equations, keep on solving them and then solving for the underlying parameters, okay. So, we will take up one particular example of AR model of order 1. So, this is my AR1 model structure, right. So, this is AR1. So, yt equals phi yt minus 1 plus et. Now, again if you go long back to one of our earlier lectures where we kind of elaborated more about AR1. So, from that lecture you can actually borrow a couple of facts. So, if you talk about correlation, so rho 1, so correlation is nothing but phi, which is this coefficient here, okay. So, correlation happens to be exactly equal to phi, okay. So, using this idea we can quickly create an equation. So, phi hat would be nothing but rho 1 hat, because phi 1 equals or rather rho 1 equals phi, right. So, the estimated versions can be replaced by the actual versions here. So, phi hat would be nothing but equal to rho 1 hat, and the formula that you see here is nothing but a sample version of the correlation, isn't it, because this is summation yt minus y bar into yt minus 1 minus y bar divided by the variance, the underlying variance, right. So, this is my sample correlation, and then you basically equate the sample correlation to something like phi hat in this case, and then solve, okay. So, in such a technique you can actually equate a set of equations and then keep on solving for the underlying parameters, okay. Now, on the other hand, we actually know a few other things also, right. So, let us say the error variance. So, by the way, this is one more parameter in any model. So, be it let us say AR1 or AR2 or any other model, you also have this variance of the errors. So, this is another parameter, right. So, again if you come back to the AR1 structure, so if you see this AR1 model structure, you have this error term here, isn't it. So, ET. So, there must be some variance of that ET, which is given by sigma square E, and sigma square E is another parameter for us. So, in fact, one needs to estimate both the parameters. So, phi as well as sigma square E, okay. So, if you want to estimate two parameters, how many equations would you require? You would require two equations, right. So, this is one of them, right, and then the other equation comes from this fact, by the way. So, but we know for a particular AR1 model gamma 0. So, gamma 0 is a variance now, right. So, gamma 0 is nothing but covariance of yt and yt, which is nothing but variance of yt. So, from earlier lectures we know that the variance of an AR1 model is nothing but sigma square E divided by 1 minus phi square, right. So, here we can replace the estimated version. So, sigma square E hat would be nothing but 1 minus phi square hat into gamma 0 hat. So, if you cross multiply, if you bring this on the right hand side, then this is the equation that you have, right. And now I can essentially replace my gamma 0 hat, because gamma 0 hat is the estimated variance of the AR1 model, right. So, that I can replace by the sample variance, which is 1 by n summation yt minus y bar square, okay. And then basically now I can replace my phi hat by rho 1 hat, which we saw from the earlier equation, right, because phi is nothing but rho 1. So, I can actually replace phi hat square by rho 1 hat square, okay. So, the value for this estimator here in terms of variance or the error variance is nothing but this 1 minus rho 1 hat square into the sample variance basically, alright. So, here we talked about method of moments or in particular Yule Walker, right. Now, the next idea is MLE, so or maximum likelihood methodology, right. So, here we require some assumptions that let us say the error vector or all the random errors, they follow some normal distribution again. So, let us say mean is 0 and variance is sigma square e, and on top of that all these errors are also independent and identical, right. So, these are some assumptions that we require. Now, the idea is that again like we discussed in the last lecture, what exactly you mean by likelihood? So, likelihood is nothing but some sort of a joint density or joint distribution, okay. Now, the whole question is, can we actually use the joint distribution applied on the actual time series values? So, something like f of y1, y2 up to yn. So, by the way, this joint density cannot be broken down into product of marginals, and why? So, why do you think? So, again the idea is that if you use the joint density of the actual time series values, right, or the observation. So, y1, y2, y3 up to yn, would this be equal to let us say the product of the marginals. So, f of y1 into f of y2 into dot f of yn, would this be true? The answer is no, because these are not independent, right. So, since yi's are not independent, this equation does not hold true, right. So, this is not equal to. So, then can we somehow simplify the problem? The answer is yes. So, instead of looking at the actual time series values, we can look at creating a likelihood function or a joint density based on the errors, because errors are independent, right. So, rather than using the actual y values, we can actually use the e value. So, E1, E2, En, and here clearly we can write down this equation, because all the errors are independent as per the assumption, okay. So, this joint density, which is nothing but the likelihood, can now be broken down into product of the marginals, right. Now, again you may ask that why do we require this? I mean, why do we require any joint density to be broken down into product of marginal? Just for simplicity, just for simplicity. So, we need not make the problem too complicated, right. So, if you are able to kind of break down the joint density into product of the marginal density, then why not, right. I mean, we have an advantage here, okay. So, this is the idea, and now so we write down the conditional log likelihood. So, why conditional? We will talk about that, but then as discussed even in the last lecture, we somehow get hold of a log likelihood function, and by the way all these are the underlying estimators or the parameters need to be estimated, right. So, mu, phi, theta and then sigma square e, okay. And then probably as seen from the last lecture, can you recollect this formula here? So, the log likelihood takes this form. So, minus n by 2 ln of 2 pi sigma square e minus a certain sum of squared residuals divided by some constant, okay. But here I am putting a star just to denote that this S star is some sort of a conditional sum of squares and not exactly the sum of squares. And why conditional? Because when you are finding MLEs using some numerical approximation kind of a technique, you have to kind of fix some starting values of the parameters. So, I am not sure how many of you have taken a numerical analysis course where let us say you have all these Newton-Raphson technique or all these convergence techniques, right. And if you are applying any convergence techniques or numerical approximation techniques, you have to consider some starting values of the parameters, right. So, once you feed in those starting values to the algorithm, then the algorithm runs and then it gives you all the estimated values once the algorithm kind of converges, right. So, this is the idea behind Newton-Raphson or for that matter any other convergence algorithm. So, a similar kind of a technique comes handy here. So, rather than taking the actual sum of squares, we are taking a conditional sum of squares. So, conditional why? Because so these sum of squares are based on some starting values. Okay. Alright, so once you feed in that sum of squares, so conditional sum of squares in this equation, now I can actually get hold of a complete log likelihood function. Alright. So once you have a complete log likelihood function, then the next step is to maximize, as always, right. So now at the end of the day, we can find out the estimators of all the parameters upon maximizing my conditional log likelihood function. Okay. And generally speaking, like I said, one can't solve this using pen and paper, because the structure of the underlying MLE or the likelihood function is too complicated. Alright. So the structure is too complicated in a way. So usually some numerical approximation techniques or numerical maximization techniques are needed to solve this. Alright. And here I was referring back to, let's say, Newton-Raphson or probably some other convergence techniques or some other numerical maximization techniques and so on and so forth, right. So rather than solving or rather than maximizing all these conditional log likelihood functions or likelihood functions in general using pen and paper or even using some basic codes in a software, one has to apply some numerical maximization techniques such as Newton-Raphson or something similar, right. And the moment you apply some numerical maximization technique, you require to feed the algorithm with some starting values, okay. And hence if you go back a slide, then we have this conditional sum of squares, because these are conditioned upon what starting values you feed the algorithm with. Hopefully this idea is clear. So how do you write down the log likelihood, then how do you maximize that, and then few advantages of MLE. So once you find out the MLE, so this estimator is asymptotically unbiased, efficient, sufficient and consistent for large sample sizes, right. But then again you have a problem also, that it slightly becomes difficult to deal with joint PDF, because you have to deal with joint PDF here, right, because likelihood is nothing but a joint PDF, right. So if you have a very complicated kind of a model structure, then how would you deal with the joint PDF combining all the observations and so on and so forth. So this could be a challenge here, but then nevertheless the MLE does have some exciting aspects to it, that it's basically asymptotically unbiased estimator, efficient, sufficient and consistent. Okay. Alright, so now on the other hand we have one more idea which is called as conditional least squares technique. So what do you mean by that? So conditional least squares technique. So here we will take up an example using an AR1 kind of a model structure. So let us say this is the AR1 equation. So yt equals phi 1 yt minus 1 plus et, and again the famous assumption is still there. So the errors have a normal distribution with mean 0 and variance is sigma square e. Okay. So from here I can get hold of et, right. So can you solve for et from this equation? Yes, we can. So et is nothing but yt minus phi 1 yt minus 1. Right. Now you get hold of the sum of squares of the errors. So summation et square. So summation et square would be nothing but summation of this structure, square of that. So yt minus phi 1 yt minus 1 whole square, and then this is nothing but my S star, right. This is nothing but my S star. Now what do you do? So you kind of differentiate this, right. So you kind of differentiate this, right. So the derivative of this S star with respect to phi would be nothing but this, right, and then you equate it to 0 basically, and then you solve for phi. So eventually the MLE or the maximum likelihood estimator in this case for an AR1 model would be nothing but phi hat, which is summation yt minus 1 divided by summation yt minus 1 square. So essentially this slide contains an example of how do you apply MLE for a basic AR1 model, and then this is based on a conditional least squares, right, because you're finding out the sum of squared errors, and then you are kind of taking the sum of squared errors and then kind of using that to find out the maximum likelihood by taking the derivative and then equating to 0 and eventually finding out the estimator of the underlying parameter. So by the way, here why are we taking a derivative? Because you want to maximize the likelihood, right. So if you want to maximize any function, you would want to first take the derivative of that and then equate it to 0 and then solve for the parameter, isn't it? So if you want to maximize or minimize any function, you differentiate it and set it equal to 0 and then solve, right. So this is exactly what is going on here. So you find out SSE, right, and then you differentiate that set it equal to 0 and then solve for the parameters. Okay. So, hopefully the idea about method of moments and MLE is clear, right. So, down the line we will talk more about, we will try to extend on, let us say, a few more estimation techniques when it comes to the practical session we will have towards the end of this week. And then there will be one more idea which we will cover probably in the next lecture, and the lecture after that is all about diagnostic checking, right. So, once you identify the orders, once you perform the estimation, then what, right. So, how would you go ahead and then do some diagnostic checking is what we will see next, right. Thank you.